Sure. Good afternoon, everybody. Dr. Stephen Sakalis with the Geography, Physical Earth Sciences Department, geographer. Thank you for coming on a real horror show of a day. I say that in Clockwork Orange, right? My pleasure here to introduce one of our seniors, Whitney Henson. In geography, it's such a wide discipline, very interdisciplinary, and there's lots of things that our students get interested in, and then they switch and they're interested in something else, anything from the social sciences to the sciences. And Whitney's came into our department with a lot of focus on meteorology. So starting last year, we got her involved with some work on cold air damming. So I'll let her explain what all that is and what makes her research interesting and innovative. And this is a project she's been working on for 2 years and has presented at a national conference, the AAG, the big geography conference we have each year. And research she plans to continue into graduate school. So without further ado, Ms. Whitney Henson.
Thank you all for being here. Before I get started, I'd like to extend thanks to Dr. Stephen Sakalis and Dr. Ted Kay for allowing me this incredible opportunity for research. I want to talk a little bit about some research that I've expanded on in the past year. I'm sure some of you have heard about cold air damming, or its colloquial term, the wedge. What you're seeing here is a picture of the Blue Ridge Mountains located in northern Georgia. They are very cute. So what is cold air damming? Cold air damming, as defined by the American Meteorological Society, is the piling up or complete walking of cold air approaching the slopes of a mountain barrier. The trapped cold air may influence the dynamics of the overlying air mass and may affect fields of moisture, temperature, and stability. This schematic shows the major elements that are typically present in a cold air damming scenario. These include a sloping inversion on the east side of a mountain range, overrunning warm, moist flow on either the east or west at middle levels, and a barrier check. The damming occurs at the lowest levels of the atmosphere, typically the lowest 1 kilometer. Looking aloft, synoptic scale forcing provides general large-scale upward motion and may result in precipitation. Subsequently, the presence of the underlying cold air mass profoundly affects the nature and distribution of precipitation. There are 3 main mechanisms that produce the low-level cold air mass in the initial stages of a cold air damming event. First, a cold air advection from a polar anticyclone or high-pressure system. In this case, cold air is progressing southward as it flows around the surface high pressure to the north. Second, adiabatic cooling. As the air flowing clockwise around the high-pressure center to the north is forced upward by the terrain, it cools adiabatically with the assumption that the environmental lapse rate is stable, which is typically true during the cold season. And finally, diabatic cooling. This is simply cooling caused by latent heat loss during evaporation of raindrops. Think of it as a cooling effect from perspiration. Cold air damming occurs in the vicinity of terrain barriers over many areas of the world, including the Alps of South America, the Mediterranean, and the Far East. Notice that the cold air damming typically occurs on the east side of mountain ranges as opposed to the west side. This happens because the origin of cold air is usually a surface anticyclone or a high-pressure system at higher latitudes. Surface flow around the high-pressure system forces the low-level winds against the east side of the mountains. For this presentation, we will concentrate on the 2 specific mountain chains in the U.S., the Rocky Mountains in the west and the Appalachians in the east. Our research places emphasis on Appalachian setups. The process begins with the passage of a cold front that brings initial shot of cold air. High pressure then moves east in the wake of this front, settling across the New England states. Now remember that winds flow clockwise in an area of high pressure. In this case, winds are coming from the east-northeast, so cold air is being forced into the eastern slopes of the Appalachians. Since cold air is heavy and dense, it is not able to lift over the terrain to disperse over the country's midsection. Instead, the air is forced southward, and the wedge of cold air flows parallel to the mountains, all the way to the south. Warmer air closer to the coast creates a nice boundary where the cool air can funnel down into the Piedmont. The cooler air flows slowly south and eventually enters areas such as northwest Georgia and parts of northeast Alabama. The effects of cold air damming in the south are commonly known as the wedge. I'm sure you guys have heard that terminology from operational meteorologists. This is due to U-shaped isobars adjacent to the eastern slopes of the Appalachians. You can see in that schematic the wedge-shaped signature of cold air. So as to dew care, when cold air damming establishes itself in these areas, a forecaster can be faced with quite a challenge, one that can wreak havoc on forecasting high temperatures and precipitation types. Often this can last for several days, and those under the wedge of this cool air can stay relatively cool, cloudy, and in most areas rather dreary. This is a radar image from an icing event about 2 years ago in December. The pink shading indicates an area of mixed precipitation, such as freezing rain and sleet. And you can see that wedge shade. So what about us? Alabama receives the effects of cold air damming or cold air drainage. Frigid air from the northeast gets a one-way express to the southeast, and a disturbance may bring rain into this area. And this disturbance mixed with cold air can bring freezing rain or sleet, often going unforecasted. So it's very frustrating. When the cold air is very deep or has strong forward momentum, it can extend as far southwest as northern and central Alabama, places like Birmingham. This is a service weather map from February 12, 2014. I'm sure many of you remember this day as Snowmageddon. Can you spot the U-shaped isobars? This was a classic cold air damming event. Last year, on February 12th, cold air damming strengthened across eastern Alabama, leading to widespread freezing rain and ice accumulations of a 1/4 inch to a 1/2 inch. This resulted in significant damage in several areas, including Mount Cheaha State Park. It's horrible. So what can we do about it? How can we, fix this? Or, be more prepared for it? The wedge can present major forecasting problems because these weather models have a hard time detecting them due to their shallow nature. Sometimes forecast models can be wrong because they don't estimate the intensity of the wedge. If it builds up, it can easily lower the temperature from 10 to 20 degrees Fahrenheit. If it erodes quickly, then we can see temperatures jump from 10 to 20 degrees as the shallow layer of cold air retreats. So it's really tricky stuff. Since the Appalachians in northeastern Alabama and northwest Georgia only average about 1,500 to 2,000 feet, the wedge doesn't really occur above that level because it's so dense. This sets up a temperature inversion where a pool of warm air resides over a layer of cooler air. This image shows a cross-section of temperatures from Meridian, Mississippi to Atlanta, Georgia. Notice the cold air wedge below 2,000 feet stops around Anniston, the pink being the cooler area. Our question and methods for this research include to what geographic extent does cold air damming influence Alabama? And how long do these events typically last? In selecting our sites, we selected 6 cities in central and northern Alabama with their own independent National Weather Service daily summary. This came out to be 14 cities total. We gathered our historical weather data from wonderground.com, who receives their information from the National Climatic Data Center. We recorded the following variables for these 14 selected cities. This includes temperature, both the actual high and the average high, pressure in inches of mercury, visibility in miles, wind in miles per hour, and wind direction, precipitation in inches, and the modal condition from that day. That's just whatever happened the most. This is a sample of our data. You can see each of our variables laid out for each of the 14 cities. Notice how the actual high temperature is far lower than the average temperature, and also notice the conditions, the dreary, overcast, mostly cloudy. And this is the corresponding map from that day. And can you spot the wedge? High pressure in the northeast, U-shaped isobars, and you also have low pressure coming in from the Gulf that can often cause a barrier jet. Here we have a map of the results so far. This map shows the daily high temperature drop from the daily average. Each of our selected 6 cities represent these counties. This is why the counties are shaded rather than the cities, also so you and I can see a little bit better. You can see how the wedge greatly affects the daily high of places further north and east, like Fort Payne and Anniston. And the further away you get from these areas, the less affected you are. But remind you, this is a representation of only the temperature. No other variables are displayed in this map. I want to look back on the event from last year on February 12th. Like I said, this was a classic cold air damming event, but we pointed out some interesting observations. Take a look at the isobars of constant pressure. Notice that the winds are blowing perpendicular to the isobars. Or orthogonal to the isobars, so like at a 90-degree angle, from high to low pressure, instead of parallel to them like they normally do. This is because of the blocking in the Appalachian Mountains. There's the U-shaped isobars, there's the winds blowing orthogonal to those isobars. It's pretty interesting. So, in conclusion, let's review the who, what, when, wheres. What is cold air damming? It's a phenomenon that involves a cold air mass becoming entrenched along the slopes of a mountain range. Where does it happen? Cold air damming typically occurs on the east side of a mountain range, anywhere in the world where there is large terrain. When does this occur? For the Appalachians specifically, cold air events occur most often during the winter months, from December to March, with a minimum in July. Winter events also typically last longer and are much, much stronger than their summer events. How does this affect us? Why do we care? Here in Alabama, cold air damming generally causes locally low temperatures, sleet, snow, freezing rain, fog, haze, and dreary days. How long does it last? A typical cold air damming event can last anywhere from 1 to 3 days. General characteristics include cold air in the form of a dome accompanied by U-shaped pressure ridges in the sea level pressure field, otherwise known as the wedge, so watch out for it. And at this time, I will take questions.
Questions for Whitney? Very good. Very nice presentation form with all your video and
Thank you.
very